And the next speaker would be Zhehua Zhou from University of Alberta. So when I'm introducing the speaker, Zhehua, would you like to start sharing the screen?
Yes, sure.
The next speaker is Zhehua Zhou. He's a postdoc at the University of Alberta. His research focuses on safe reinforcement learning and control theory in robotics. He received his Bachelor of Engineering degree in mechatronics engineering from Tongji University, Shanghai in 2014, and the master degree in electrical and computer engineering from the Department of Electrical and Computer Engineering, Technical University of Munich in 2017. He earned a PhD degree from Technical University of Munich under the supervision of Professor Martin Bass in 2022. The floor is yours, Zhehua.
Okay, thank you very much, Professor, for the introduction. And I will begin. Okay, so hello everyone. My name is Zhehua Zhou, and welcome to my talk. Today, I will present to you our work that is about safe reinforcement learning with model order reduction techniques. So I'm currently a postdoc researcher at the Momentum Lab from University of Alberta, and our lab is in association with the AMI, which is the Alberta Machine Intelligence Institute. So the focus of our lab is to understand and bridge the gap of theory and system while using engineering concepts. So we try to build a safe, reliable, and secure AI system. So based on that, one of the most important research interests of our lab is the so-called safe reinforcement learning. So this is inspired by the fact that we have observed many impressive results of reinforcement learning or deep reinforcement learning in robotics. However, in the meantime, we also find out that there are actually less real-world demonstrations. So one major reason for this is that due to the random exploration mechanism of the learning algorithm, the intermediate policy might be very risky, not only to the system itself, but also to the environment. So we want to have a learning algorithm that is able to learn while satisfying certain safety constraints. So in that regard, we see that a safe reinforcement learning approach is desired because it can bring learning-based controllers to real-world applications. So when we're talking about learning, safe reinforcement learning in robotics, we usually consider the approach that is done by combining learning approaches with control theory. So we use learning to do the controller design so that the system is able to accomplish how to engineer behavior. But in the meantime, we also want to use control theoretical concepts to keep the learning process safe. So the final goal is that we want to have an intelligent controller design approach so that we can solve complicated control tasks. And we also want to bridge simulation and reality so that the proposed method can actually be applied in real-world scenarios. So in literature, there are already many safe reinforcement learning approaches, and most of them focus on providing theoretical guarantee. For example, one important aspect is the safety during exploration. So for instance, the work from Physically, it used the reachability analysis to predict the system behavior so that the system can do the reactions accordingly and do the exploration safely. Another example is the work from Beckenham, which uses the region of attraction to define a safe region. Then the exploration is limited in the safe region so that the learning process is safe. So these two works also give us the inspirations on formulating our own approaches, which I will talk about later. And of course, there are also other aspects, for example, modal mismatch and honor disturbances and so on. However, although there are good results of these works, there exists one challenge here that usually to get this theoretical guarantee, it requires a relatively heavy computations. So actually, this approach might only be applicable to systems with low-dimensional state space or with simple dynamics. But if you really consider the motivation of why we want to use reinforcement learning to do the controller design, it's often the case that we want to overcome the drawbacks of traditional controller design techniques. So in that case, we often consider the practical system are actually highly nonlinear and high dimensional. So in this case, unfortunately, these approaches are hard to implement or even infeasible to be implemented due to computational cost. So new approaches have to be proposed. So taking from that, our focus is that we not only put focus on theoretical guarantee, but we also want to put more focus on the practical realization of the safe reinforcement learning approaches, especially for complex dynamical systems. So we consider applicability and generalizability of the approach so that it can be applied to a wide range of different dynamical systems and to different learning tasks. We also want to include the learning efficiency so that the learning performance will not be overly affected by the consideration of safety. So this is our focus, and to do that, we basically formulate our own approach by using the idea that is called supervisory control. So the basic idea is simple, that we say if we have a general nonlinear system in this form, and if we can find a forward invariant safe region S for this system, then we can simply introduce a supervisor to the standard reinforcement learning loop. And this supervisor switches the actual applied control action between a learning-based controller and a corrective controller. And this switching happens when the system approaches the boundary of the safe region. So by doing so, the exploration is safe as long as the system state is inside the safe region, because there always exists a valid control sequence to drive the system back to a safe state. So this is the basic idea, which is simple and straightforward. But unfortunately, for complex dynamical systems, it is usually quite difficult to directly compute this safe region. So what we do is that we want to introduce the idea to use so-called simple to predict hard. Then this refers to the so-called model order reduction techniques. So this kind of idea is actually widely used in engineering problems. So for example, if you consider the control problem of a biped robot, then the direct control on this fluid dynamics could be quite challenging. So what the researchers do is that they introduce a simplified model, for example, an inverted pendulum model. Then they first do the control on the simplified model and then try to transfer the policy back to the real system. So the idea is the same. So we want to use a simplified system to predict this hard to compute real high dimensional safe region. So based on this idea, I will briefly introduce you two of our works that both lead to a general safe reinforcement framework, and one work is based on physically inspired model reduction, and the other is based on the data-driven model reduction. Okay, so the first one is safe reinforcement learning with physically inspired model reduction. So for this one, we assume that we can find a simplified system model in this form while physically inspired model reduction. So basically use essential physical features. And this simplified system model has a low dimensional state space. Then we can basically map each high dimensional system state to a corresponding low dimensional system state. And this simplified system state will predict the safety of this high dimensional state. So we also see that the safe region of the simplified system is relatively easier to compute due to the fact that it has a low dimensional state space, so that we can use this simplified safe region to predict this original high dimensional safe region. But to do this kind of prediction, we also have one assumption regarding the property of the simplified system model. So the assumption here basically states that if we observe a safe original system trajectory, then it should also correspond to a safe simplified system trajectory. So if this assumption is valid, then we can simply use the simplified system to predict the safety of the original system. So basically, the simplified safe region provides belief about the original safe region. So this is the general idea, and based on that, we provide a safe reinforcement framework, and the overview is given here. So the first thing we do is to use the essential physical features to construct a simplified system model and to initialize the belief about the safe region. And of course, this initialization is inaccurate, so we also want to update the belief during the learning process. So this update, we use what we call the feedback data, which is the actual execution results of this corrective controller. And this online update method is based on the so-called belief function theory. So for this update part, I will now give you some more details. So to do the online update, we've introduced the belief maps, what we call as belief map, for representing uncertainties in making safety estimates. So to create this belief map, the first thing we do is to discretize the simplified state space, and we assume the probabilities are the same within each grid cell. Then we can predict the safety of an observed system state by using its corresponding simplified system state. But note here, due to the order reduction, different system state may map to the same simplified system state. So this safety estimate is given in the probabilistic form. And using this probabilistic safety estimate, we can assign a basic belief assignment to each grid cell, which contains 3 elements. The first 2 elements are the probabilities of the occurrence of 2 complementary events. So basically being safe or being not safe. Right? Then the third element is the uncertainty in making such an estimation. So by combining this basic belief assignment among all the grid cells, basically among the entire simplified system state, we will get one belief map. Then we actually construct two belief maps for representing 2 different types of uncertainties. So the first one is the prior belief map, which means the uncertainty comes from the simplified system model. So this one is fixed during the learning process because the simplified system model is fixed. And we also have another feedback belief map, which means the uncertainty comes from the limited number of available feedback data. Then these 2 belief maps are fused through an operation that is referred to as weighted belief fusion. This will lead us to a combined belief map, and this combined belief map satisfies the property that it will converge to the actual probabilities if enough feedback data are provided. So this is the general idea of this safe reinforcement learning with physically inspired model reduction. Of course, I have to skip some details due to a time limit, and if you have interest, we can talk about them later. But right now, I want to give you an example of the performance of this framework. So we basically consider here a quadcopter flight control example. We say the learning task is flying while tracking a given constant reference velocity, and the safety is prevent crashing during the learning process. So the learning-based controller is a simple PPO algorithm, and the corrective controller is a PID controller on board. So we do this experiment both in simulation and in a real-world experiment. And due to time limit, I will just quickly show you the video of this real-world experiment. So the task is basically track a given constant reference velocity, so basically fly forward. Then in the initial learning phase, so as you can see, the learning-based controller will be immediately stopped and the corrective controller will be applied. This is due to a conservative initialization of the estimation of the safe region for keeping the system safe, basically. And with the learning goals on, this safe region will be expanded, and the learning-based controller will have more freedom in choosing its actions. For example, here, as you can see, the learning has more aggressive actions, but this is still very dangerous, so we'll try to prevent crashing during this learning process. And with the learning goals on, we will have a better final performance. And this is how this combined belief map, basically the low dimensional safe region looks like, and how it is updated during the learning process, how it is expanded. So basically, this is the results for our safe reinforcement learning framework with physically inspired model reduction. So we also have another work that is based on data-driven model reduction. So the motivation for this work is that the determinative physical features are not always available. So for certain tasks, it is quite difficult to pick the right and representative physical features. So we also want to introduce this data-driven model reduction. it has the benefit that it is really efficient in computation, and it usually has a higher flexibility and applicability because it usually only requires data to do the auto reduction. But to do this, we will need some offline training data. So we will need something in the simulation, and the focus is therefore transferring from simulation to reality. So for this one, we also have a slightly different problem setup. So for this one, we assume that the node information of our system provides us a nominal system model. So basically this one, but the real system has an unknown part, and this unknown part will cause discrepancy between the nominal and the real systems. But still, we can try to use this nominal system for doing the simulations and to predict the behavior of the real system. So this will give us the training data for estimating the safe region of the real system. Then in this setup, the focus is the safety during transferring policy. So basically from nominal system to real system. So from simulation to reality. So based on this idea, we also gave a safe reinforcement learning framework. On the left-hand side, it's the initialization phase with data-driven model reduction. So we will need a training data set. Then we try to find a low-dimensional safe region, SL here. Then this low-dimensional safe region approximates the high-dimensional safe region. Then we also want to update the safe region online with, again, belief maps. But one difference here is that we also, in this case, estimate the reliability of training data. So we try to predict how trustworthy is our training data. So how close this nominal system is to the real system. And these two belief maps are fused again through this weighted belief diffusion for having better safety estimates. So here I will again give some more details. So for the initialization, we will need some training data from simulation, and by training data, it includes first the system trajectory as well as a safety label. So basically this one here, which indicates that if it is a safe trajectory or not. Then we can compute trajectory similarities, for example, this omega 1,2 or omega 1,3. Then once we have this trajectory similarities, we can introduce data-driven method, for example, t-SNE, to find low-dimensional safety features. So basically, a similar trajectory will give closed simplified system state, and dissimilar trajectories will give distant simplified state. Then by using these low-dimensional safety features, we can try to identify a low-dimensional safe region in this simplified state space. And this initialization is then purely based on the training data. Then to overcome this discrepancy between the nominal and the real system, we also do the online update. Here we use a similar idea as this physically inspired model reduction framework. So we use, again, belief maps for representing uncertainties. We will have a prior and a feedback belief map. So the prior is for training data and the feedback is for feedback data. But here, as I mentioned, we also want to estimate the reliability of training data. So we use observed data to create a Gaussian process model. And this model predicts that how close our trajectory of the nominal system is to the trajectory of the real system. Then based on this standard deviation of the prediction, we try to assign different uncertainties to each training data and use the updated training data to update the prior belief map. Then the updated prior belief map is again fused with feedback belief map through this weighted belief diffusion for having better safety estimate. So this is the general idea. Again, for more details, we may talk about them later if you have interest. So I also want to give results of this data-driven one. So we still consider quadcopter control. So the original state space is a 12-dimensional system state, and we want to reduce it to a 2-dimensional safety feature. And this is the results after the initialization. We will have a safe part and almost unsafe part. Of course, this initialization is inaccurate, so we also want to have some update. So for this one, we see the real system has only 80% of the mass and 70% of the max lifting force. Then we update this initial low dimensional safe region with feedback data. And this is how the update looks like. As you can see, the color is changing, and we use red color for being safe and the blue color for being unsafe. So the central part, this part becomes the region that we believe the real system will highly likely be safe. So this low dimensional safe region can then be used to guide the learning process. So this is the results and the general idea of the model reduction, this data-driven model reduction for the safe reinforcement learning. So to conclude my talk today, I briefly introduce you the safe reinforcement learning framework for complex dynamical systems. And the one uses physically inspired model reduction, and the other one uses data-driven model reduction. So the framework is efficient in implementation and compatible with arbitrary reinforcement learning algorithm. And the framework is also generalizable to a wide range of different learning tasks and different systems. So for future work, the first thing we want to do is to consider the possibility of using projection-based model reduction. So this one usually requires a more complicated computation. But if this can be done, then we will have more reliable safety guarantee and the learning efficiency. So this is due to the fact that a stronger connection between the original system and the simplified system can be established through this projection-based model reduction. And the second possibility is that we want to probably measure the similarities between different dynamical systems so that we can hopefully transfer the learned safety features from one system to another system. This will then accelerate the learning process. So we also want to check the applications of the framework to different tasks, for example, how to extend to multi-agent system or to extend to some advanced control tasks. Okay, I think that's the content for my talk. I would like to thank you for your attention. And if you have questions, maybe.
Thank you. Thanks, Zhehua, for the fantastic talk. Let's see whether we have questions from the audience. I might have a question. So basically, I noticed you mentioned that you're training the agent in a nominal system, and it receives feedback from the real system. So how frequently would you need the feedback from real system, or like in general, how is the sample efficiency in this query to the real system?
Yes, thank you for your question. So here, during the learning process, this feedback data is accumulated. So each iteration you accumulated the feedback data, but this update process, you can define how frequently you want to update. So for example, here, each step we use like 20 feedback data. So it's kind of the user-defined parameters. So if you have a low number, then you will need more resource, more time spent in the update phase. But if you have a larger number, then you can do this update in a low frequency. But then you will have some out of date low dimensional safe region. Then you have a higher risk. If you have a larger discrepancy, then you may have a higher risk in having these failures. So I think it based on the estimation of how large this discrepancy is. If you believe it's gonna be quite high, then you can use a more frequent update, I guess. Yeah.
Okay, thanks. I was wondering, how does this framework relate to the model-based reinforcement learning or model-based policy optimization framework? Because it has like learns the model based on the data, learns the update the nominal system based on the feedback from the real system. So do you see the connections or difference here?
Yeah, so what we learn here is directly so for this one, what we learn is actually the data about this safe region. So not the behavior of the system. So for complex dynamical system, it usually require more data and a more complicated model to learn well-performed system model. So here, what we learn is only one safety feature. So it's only one safety label, let's say. Then it can be easier because if you have a full system model learned from this model-based reinforcement learning, then in the update part, you will need update a more complicated model which require more feedback data. So we try to reduce this problem if you want to use it on a high dimensional and highly nonlinear system. We will try to overcome this requirement on the resources. So we only need this safety label. But of course, a better system model can be quite helpful because then you can verify if this safety label is reliable from your nominal system or not.
Okay. Thank you. Thank you for the answers.
Thank you for your question also.
Okay, how do you define the safety label?
Yeah, it's more like a user-defined thing. So in our experiment, we simply define that, for example, for the quadcopter example, we say if the current state from an initial state, if the quadcopter can be safely controlled back to a safe hovering state. So then if it can be controlled back to there, you will have a trajectory of the system state, as well as a label indicates that, okay, this initial state is safe. But you can, of course, define based on your task. So this one for here, we use for our work, we use the so-called region of attraction. So if it can be safely driven back to a safe equivalent point, then we say it's safe. But if you have more requirement on safety, for example, collision avoidance, you can use some different formulation. For example, that there's one idea from this Lyapunov and barrier function, which you can include some obstacle in formulating this safe region. So basically, you can try to adjust this definition here by considering which task you are actually trying to accomplish.
Okay, I have other questions. Maybe we can discuss it after the workshop. Okay.
Yeah, sure.
Yeah, thank you, Zhehua. For the time's sake, I think we might close the discussion here and move to the